Okay, this is the video for section 13.7 on the tangent plane and normal lines. We started talking about that last class, and the idea, again, is to try to approximate a function that is quite complicated, a smooth function, and approximated by a linear function or plane. So it's always good to see what we have in one dimension. So let's say I have a function from R to R. Okay, this is the graph of the function. That's not the input. Okay, that's the graph. So x-axis is the input, y-axis is the output. And so this is the graph of the function. It's quite complicated. And if I look at a given point x0, and then if I zoom in, like this, and the function flattens and flattens, right? I don't see it oscillating back and forth, up and down. And so we want to capture this linear behavior, and that's called the tangent line. So the tangent line at the point x0, fx0, the xy plane, as we know, is f prime of x0 times x minus x0 plus fx0. So that gives me the slope. All right, and if I want a line, so y equals mx plus b, that's the b if I want the right output for the input x0. So that's a linear function of x. All right. Now we saw that we can, so that's if you want the line when it's parametrized by x. We can also parameterize it and write it in terms of direction like what we did in space, right? So I need a direction and a reference point. So let's say I parameterize my line by x equals t plus x0, so that t equals to 0. I'm at the point x0, and y then, right, is what? Well, that's what I wrote, so it's f prime, now x minus x0 is just t, plus fx0. Okay, so this is my parametric equation. Okay, and once I have my parametric equation, it's easy to write it as a direction and a reference point, right? So everything that is in t here, so in the x coordinates, I get just 1. Here, f prime of x0 plus x0 fx0. So that's my reference point, x0, y0. And the direction, well, it's the multiple of that vector. So I should write it here. That's the reference point, and that's the direction of my line, okay? And in other words, if I go one step in the x direction, then my output increases or decreases by f prime x0, okay? All right, so it's the rate, f prime is the rate of increase or decrease with respect to x, okay? So that's what the unit is 1 here. Now, what about the normal line? Well, you also did that in Calc 1. Okay, so now what I want is the line that is perpendicular, okay, to this orange line and also goes through the same point. So remember that for a line, I need a reference point and a direction, so the reference point is clear. It's x0, y0, or fx0, x0, fx0. And the direction, well, has to be perpendicular to the direction of the line, tangent line. And therefore, I need to find a w such that dot product with the direction of the tangent line is 0. Okay, so if w is equal to ab, that's equivalent to say that a plus b f prime of x0 is equal to 0, or in other words, b is equal to minus a f prime of x0. Okay, so the directions is all multiples of 1 and then minus 1 f prime of x0. Okay, so let's write it. So this w, so if I parameterize my tangent line by s, the direction is 1. Okay, I choose a equal to 1 if you wish. And then you do this minus 1 divided by m. You must have done several times in Calc 1. That's where it comes from. It's because I want the dot product to be 0 times s plus x0 fx0. And then if I just want y equals mx plus b, well, that would just be the y coordinate. All right? So that's what we do to find the tangent line and the tangent and the normal line. Now note that you can do the same thing when you have not a graph of a function, but a curve whose graph is not necessarily a function, okay? And that is given by an implicit function. So how do you do this? Well, let's say take the unit circle. You can find by the chain rule y prime of x. If you take y explicitly as a function of x, and you get by implicit differentiation that y prime is minus x over y. Of course, this holds when y is not equal to 0. Y is equal to 0, the derivative is infinite. So actually the normal line, or tangent line, I should say, is simply the vertical lines. All right, that's a review of Calc 1. Now, how do we do this for a function of 2 input to r? So what we're going to get is not a tangent line, but it's a tangent plane. All right, so we start doing this. So remember when we looked at differential at the last lecture, I did an example of differential. The point of the differential is to look at how the function vary at first order of approximation. Okay, and what we got using the partial derivative, we can write it compactly as saying that fxy in a neighborhood of a point is equal to the function at that point, that's the 0th order, plus the gradient at that given point times dot product with the vector x minus x0, y minus y0. So how much I move away from the reference point, plus some error, okay? So what plays the role of the linear function now is this, okay? So the value of the function at the point plus the gradient dot product with this vector, okay? And so that's my linear function, and I can write it if I expand the dot product and write the gradient explicitly as del x of f at the given point times x minus x0 plus del yf at the given point times y minus y0 plus the value of the function at the point, okay? Now this is the function of a plane, so I know that. Why? Because it's simply a linear function of x and y. Those are the only variable, okay? All the x0, y0, it's a given point. We'll do examples, so they're just numbers. So it's just a function of x and y. It's a linear function of x and y at that, okay? So that should give me a plane, okay? So how do I see concretely, so what's the equation of the plane in the standard form we used to do, okay? Well, what I do is see the output of that linear function as the third coordinate, z, all right? So the third coordinate is equal to that, okay? Now, if I write this more in a different way, now the value of the function at the point x0, y0, let's just write it z0. And then if you just massage this, okay? So this is obviously a dot product. We had that before. But I can also write, if I send z the other way, this becomes z0 minus z. So I can just write this as a dot product of the xy coordinate. Then I add the z coordinate, all right? And that's the form we had of a plane, for equation of a plane, okay? So this is the vector if you move away from x0, y0, and you want this, so all vectors, those are all vectors on the plane, you want this to be perpendicular to the normal vector, remember? So we know this is the equation of the plane. I wrote it in standard form. So what do we conclude is this is the normal vector to the tangent plane, okay? So del xf, del yf, like the gradient, and you just put -1 for z, okay? If you don't like that, if you wanted a 1, then you can just multiply by -1. If a vector is perpendicular to the plane, then minus that vector is also perpendicular to the plane. Okay, so it's similar to what we have in 1D. In 1D we had, let's say 1 f prime. Well, now there's a 1, 2, and the partial derivative. Okay, so if you want the equation of the tangent vector to a plane, a tangent plane to a point, you just compute the partial derivative and you add -1, and then you multiply. You do the dot product with this vector. All right, that gives you the equation in the standard form. All right, so that's the bottom line. Okay, again, the tangent plane at a given point of f as equation, here I wrote it is z. The third input is the gradient dot product this vector plus the value at that point of that function. And if you want to write it, that's in terms of x, y, z, then it would become that form. All right. Now, what about the normal line at a point x0, y0? Well, I know the normal vector. So the normal line are just multiple of that vector plus the reference point. So that's very easy. The line, okay, with coordinate xt, yt, zt are all the multiples of the normal vector to the plane plus the reference point. Okay? Let's do a quick example. I have a hyperboloid, hyperbolic paraboloid, x squared minus y squared. I want the equation of the tangent plane at 1, 1. And also I want the equation of the normal line at the same point. All right. So how can I do this? Well, first thing to do is always to find a gradient. At a point xy is just 2x minus 2y. If I evaluate it at the point 1, 1, this is just 2 minus 2. Okay. Now I like to actually write this first in terms of f of xy, okay, is equal to the function at the point 1, 1. If you plug it in, that's just 0. That's the 0th approximation. And then I get the linear part, which is just the gradient time dot product with the vector x minus 1 and y minus 1 plus some error. All right. So that's the equation of the linear approximation. Is just, since this is 0, I get 0. 2x minus 1 minus, I'm doing the dot product here, minus 2y minus 1. So if you simplify it, it's just 2x minus 2y. Okay? So this is the equation of the tangent plane, looking at the third coordinate. So z is equal to 2x minus 2y. I could put everything on the same side and write it, if you want, as z minus 2x plus 2y is equal to 0. All right. And if I want the normal line, well, I just put 2 minus 2, that's the gradient, and then I put minus 1, okay, as I did before. So the normal lines are all the multiple of that normal vector to the plane, plus the reference point, which is 1, 1, 0, because x, y is 1, 1, and z is 0. Okay? So that's the equation of the plane at that point and of the tangent plane and of the normal line. Okay. Last thing, we'll do more example. This class is the equivalent of looking at the tangent line for the circle. So what about my surface is given by an implicit equation, okay, like we have for some quadratic surfaces. Okay, so for example, for the sphere. So how can I do this? Well, here's the recipe, and I'll discuss that in class and explain a little bit more why it works. Okay. So this is actually a level surface, okay? So it's the three-dimensional equivalent of a level line, okay? And this is the surface of the function x squared plus y squared plus z squared when this function is equal to 1, okay? So those are all the points x, y, z for which this function is equal to 1. That gives you a sphere. And therefore, this is a function of three inputs, and I can take the gradient. I just have three derivatives. So I get 2x, 2y, 2z when I do the partial derivative of that. Okay? And it turns out, and this you have to accept at this point, that this vector is perpendicular to the surface. Okay, so that gives me the normal vector, direction of the normal vector, exactly like the gradient is perpendicular to the level lines. I'll prove that next class. So I have the normal vector, it's very easy to compute, and therefore if I want the equation of the tangent plane, what do? Well, I take the dot product between x minus x0, y minus y0, and z minus z0 with that normal vector. And that gives me the equation of the tangent plane. And so the recipe is quite easy. Okay, now I'll explain why this is actually normal vector to the plane. Okay, and also I will explain next class a different way of doing this, getting this equation using parametric equation. That is, I find two direction in the tangent plane. All right, thank you for listening.